Hey, it's a pleasure to welcome Victor Acosta from University of New Mexico, who will be talking today on diamond quantum sensors and will inform us on the sensitivity frontier. Victor got his PhD at Berkeley in 2011 before going on to do a postdoc at Hewlett-Packard Labs for 4 years, where actually we overlapped for maybe 6 months, and then worked at Google Life Sciences before becoming a professor at the University of New Mexico. He is an expert in diamond-based sensors, and excitingly for our department, on applications of these sensors, which range from biomedicine all the way to detecting dark matter. So I'm excited to learn more, and let's welcome Victor. Thanks.
Okay, thank you, Kaime. How's the sound? Is it okay? Good, okay. Thank you so much, Kaime. It's a pleasure to be here. Thank you all for coming. And I'm going to talk about this research field that we have been investigating at my lab in the University of New Mexico. So I like to start, especially with all the quantum hype that we've seen the last few years, I like to start with a definition. I'll just point out this is the definition of quantum sensors. It's not the same definition that I would have used when I was a graduate student. And it's not necessarily the best definition either. It's just a definition that I'm going to use for the rest of this talk, so that kind of everybody knows what I mean when I say the phrase quantum sensor. So what is it? Well, if I were to say it in just like a few words, it would be to use a qubit to detect things. And it comes from this Review of Modern Physics article from 2017, where the authors identified a list of criteria, kind of an analogy to DiVincenzo's criteria for a quantum computer, but now for what defines a quantum sensor. And they are as follows. So the first is, we said we're going to use a qubit to detect things, so we need to have at least two discrete energy levels, which will define our qubit with a transition, E equals h nu. We need to be able to initialize experimentally the qubit into an individual state. And then we need to be able to coherently drive the qubit into arbitrary superposition states and then to read out the qubit quantum states via some sort of external driving, like an optical or a microwave or a radio frequency field. And then lastly, well, it's a sensor, so the qubit states need to evolve coherently in response to some environmental parameter that we're going to try to measure. Notice I use this word coherently a few times here. Turns out that that's a particularly important property for determining the sensitivity of our quantum sensor. We'll talk a little bit about it in a second. Okay, so by this definition, the system that is near and dear to my heart because I started it during my PhD qualifies as an early quantum sensor, namely alkali metal vapor, like rubidium, cesium atoms, et cetera. So it's quite a broad definition. I just point out that this definition is maybe unique in that it doesn't require there to be entanglement. It only requires single qubit operations. So it's a bit different from the requirements that would be needed for a quantum computer, for example. Alkali vapor have been used in a number of applications, and the most clear present one is, of course, in atomic clocks, which are the backbone of GPS systems and have been since, I guess, the late 40s, and continually miniaturized, and new products are coming out today. Magnetometers, so sensors that detect magnetic fields, are probably amongst the largest markets. And maybe within that, maybe the largest market is like the oil and gas industry or environmental monitoring. People go around with these airplanes or booms and try to look for things underneath the ground. But more recently, people have managed to miniaturize these, and that opened up new types of applications. So for example, using these magnetic field sensors to do MRI of the brain or of hands and things like this, and then something called magnetoencephalography, detecting the magnetic fields produced by the brain, which is a pretty big topic these days. Here's an example of a device being operated out of the lab in the field. And then, inertial sensors like gyroscopes and accelerometers, et cetera, et cetera. Okay. All told, a reasonably successful technology, I think, but maybe not an enormous market, like kind of at the, let's say, hundreds of millions of dollars. And you might wonder, what's missing? Why not? It's debatable, the answer. But maybe one thing that is missing is the device platform, let's say. So something that's motivated me a lot in my career in general is this idea of doing AMO, atomic, molecular, and optical physics, on a semiconductor chip. And the motivation is like, we take these systems that I studied as a physics graduate student in atomic physics, take these systems that we have exquisite control over, and maybe a canonical example is like atoms loaded into an optical lattice, where we have kind of control over the interactions of the atoms. We're able to address them individually, and these systems evolve extremely coherently, all very cool physics. But they tend to live in these kind of bulky setups. They tend to require ultra-high vacuum, et cetera. And okay, it's annoying that they're bulky, but it kind of prevents us from studying certain types of samples, because now we can't necessarily bring our sample of interest and get it very close to our qubit sensors. So the dream is something like what's pictured here. So the real dream is, let's say we have like 6-inch wafer technology to start with silicon and have like SiO, or maybe quartz, and we have like maybe a little cladding of SiO2. And on top of that, we have a thin host crystal of, like, let's say, a wide bandgap semiconductor. And then we go in and we introduce our qubit sensors in a really well-defined array with nanometer precision and pitch. And they're all living very close to the surface. And so what could we do if we had such a device? Well, one thing is that because it's in a semiconductor, we could carve all kind of like interesting electronic and photonic components into it. And then, maybe even more importantly for sensing is that because these qubits would live very close to a surface, we could picture putting samples of interest on top of them and image them with not only a high spatial resolution, but also like a high signal strength. So that's the dream. A few things to consider, especially when it comes to that host crystal that our qubits are going to be embedded in. So in a semiconductor, we have to consider the bulk crystalline states, but actually we really don't want those to be necessarily involved in our quantum sensor. So in principle, if we're using a spin qubit as our detector, in principle, the energy gap can be very, very, very small, let's say micro electron volts, and therefore almost any semiconductor could be suitable. But it turns out to satisfy this initialization and readout criteria I talked about before, it's awfully convenient to have access to an optical transition, at the level of, let's say, electron volt or so. And so, we'd like for our qubit levels to live within the band gap so that it's not interacting with the bulk crystalline states. There's a debate over exactly how far from the bands they can be. Maybe this optical transition can involve levels in the conduction band, et cetera. But for now, I'll say that because of the need for an optical transition within the band gap, this kind of tends to point towards wide band gap semiconductors. And there are lots of examples: boron nitride, diamond, gallium nitride, silicon carbide, zinc oxide, like Professor Fu studies, et cetera. I'm, of course, today going to talk about diamond. One more thing to think about, though, which is that, especially because we're going to talk a lot about detecting magnetic fields with our quantum sensor, and so we don't want the host crystal to be producing magnetic fields of its own, right? We don't want the sensor to be producing these fake signals. And that means that ideally we would have access to stable isotopes that compose the crystal that don't have a nuclear spin. And if you go through the periodic table, you can see that kind of rules out all of the group 3 and the group 5 elements. But there's plenty of choices in groups 2, 4, and 6. And then, I'm going to talk mostly about carbon today in group 4. So what is an NV center in diamond? Well, first I'll just point out that not all diamonds look like these engagement gemstones that we're all marketed about. And in fact, diamonds can take on all kind of different colors. And the reason why they take on colors is because of the impurities or the defects inside of the crystals. And for example, if you dope a diamond with a lot of nitrogen, it will kind of have this yellowish color. A lot of boron will be this blue color. A lot of hydrogen turns this kind of magenta color. And actually, it turns out that the NV center that I'll show in a second in a high enough density also shows this kind of pretty pink magenta looking color. So the NV center, yeah. So we'll take the all carbon diamond lattice. We're going to remove 2 nearest neighbor atoms here, if you can see my cursor. We'll replace one of them with a nitrogen atom, leave the other site empty or vacant, and we formed a nitrogen vacancy center, or NV center for short. Now, when it comes to single crystal diamond, we don't have access to this wafer scale dream that I showed in a previous slide, but through chemical vapor deposition or high pressure, high temperature synthesis, we can make synthetic diamonds, chips that are kind of like at the level of a few millimeters or so, which are adequate for most of our kind of early experiments. So it makes for a nice model system, at least. Diamond, it's all carbon. There's a hope that maybe that could mean that it's not toxic and that we can do some biological studies. It is a semiconductor chip. We can carve all of our favorite devices into it. And then, yeah, the NV center turns out to have optical and spin transitions that fall well within the diamond band gap. OK, so kind of the backbone for all of the quantum sensors that I've studied, at least, is something called optically detected magnetic resonance. So that's kind of the physical principle that lets us extract information about the environment. So I'll go into it in a little bit of depth. So right now, we just picture a generic atomic-like system. It's got a ground state and an excited electronic state. You can shine green laser light on it, and it will fluoresce. One of the key properties is that we should be able to shine green laser light on it for weeks and months and years at a time, and it should just continue to fluoresce just as brightly as always. That's not always so easy to do, but in a crystal, it tends to be easier. But those are not our qubit levels. So our qubit levels are going to be 2 spin levels within this ground electronic state. And so there's 2 spin levels. So if we're going to talk about magnetic fields, I'll use it as an example. It's also mostly what I use in my lab. So when we're trying to detect magnetic fields, it's a useful property that the spin up and spin down levels will split linearly in opposite directions as a function of magnetic field. And so that in principle, just by measuring the energy difference between the 2 spin levels, we can infer the local magnetic field. We need a few more properties to get this ODMR trick to work. One is that if we shine green laser light on for long enough, all of the spins need to end up into one of these 2 spin levels. That was kind of our initialization criterion before. And then the other one is that we need to exploit, there needs to be some optical property that is different for one of these qubit levels compared to the other. It doesn't need to be fluorescence brightness, although that's the example I'll use, but that could be, the index of refraction is different, the absorption is different, the polarization selection rules are different, et cetera, but we'll talk here just about the brightness of the fluorescence. So we'll say that this lower spin level has brighter fluorescence, and also if we shine the green laser light on long enough, all of the qubits will collect into this lower, brighter level. So the way we do ODMR spectroscopy is now we're going to do this experiment where we're going to continuously shine green laser light onto our qubits. We're going to measure the fluorescence brightness. Meanwhile, we're going to go in with a microwave field, and we're going to sweep the frequency of the microwave field, and we're going to plot the detected photocurrent, the fluorescence brightness. So initially, when our microwave frequency is at a very low frequency, it's not interacting with the system much at all, and as I said before, all of these qubits will collect in this bright fluorescent state and have a high fluorescence. But then as we sweep the microwave frequency, eventually it will match this spin transition frequency, and it will drive some of the spins coherently into this dimmer upper qubit level, and that will lead to a dip in fluorescence. And then, yeah, when we increase the frequency even higher, it's again almost as though the field weren't there, and the qubits again collect in this bright fluorescent state. So in this way, we can map out the spin transition frequency just by monitoring the fluorescence as we sweep the microwave field frequency. And then that can give us a measure of the local magnetic field because the spin transition frequency is proportional to the magnetic field. The width of this transition ultimately is related to how coherently can we drive these spins. So that's why this word coherence is so important. We want a very narrow spectral width here if we're going to use this as a sensor, right? It gives us the highest sensitivity. And so the more coherently the spins interact with the microwave field, the narrower this ODMR spectral peak is. Okay, we're going to talk a bit about sensitivity, especially towards the end of the talk. So I just point out that there's lots of different things to worry about when you're trying to make a very sensitive sensor. You know, some of them are just like basic lab noise, pickup, intensities of laser powers, and everything else. So let's picture that, you know, our very clever graduate students have eliminated all of the you know, technical noise in the lab. What are the fundamental limitations? And amongst the first is something due to photon shot noise. And so the way I like to picture this is like, okay, suppose now, in contrast to the previous plot, now we're going to choose a particular microwave frequency, and then we're going to sweep the magnetic field. Well, we'll see, we'll still get this ODMR dip when the magnetic field matches the microwave field frequency, but we're plotting it a little bit differently, yeah? And then we're going to further bias our system. So now we're going to choose a particular magnetic field that corresponds to being on the point of steepest slope on this curve. And then you can see here that, yeah, if the magnetic field increases a little bit, the fluorescence brightness will go up a bit. If the magnetic field decreases a little bit, the fluorescence brightness will go down a bit. And then, yeah, we have kind of a linear mapping between the fluorescence brightness and the magnetic field. That's great, but ultimately, because we're trying to detect fluorescence brightness, that means that we're ultimately counting photons. And the nature of photon counting statistics tells us that there's this fundamental Poissonian noise called photon shot noise. And so what it means is that, yeah, if we have these little fluctuations in fluorescence that already happen just from counting photons, and we can't tell those apart from real changes in magnetic field, because we have this mapping between fluorescence brightness and magnetic field, and we can't tell the difference. So if we take the kind of photon shot noise limit, we can extrapolate a minimum detectable magnetic field. And the expression looks like this. It's 1 divided by gamma. That's the gyromagnetic ratio of the spin or the qubit system. C is the kind of visibility of this ODMR peak, or the relative amplitude of it, times the square root of n sub s. That's the number of spins. Eta, that's the photon collection efficiency. T, that's the total measurement time. And T2 star, that's the coherence or the dephasing time of our spins. And remember that the dephasing time is kind of, or the width of this peak is like 1 divided by the dephasing time, T2 star. Okay, there is another limit that I'd be happy to derive for you if you ask later, but for now I'll just present it, which is that even if somehow we were able to get rid of the photon shot noise, we would be limited by the spin projection noise. So this is the fundamental statistics of detecting spin eigenstates called the spin projection noise limit, or the standard quantum limit, that sets another limit on our minimum detectable magnetic field that's equal to 1 divided by gamma, that's the gyromagnetic ratio, times the square root of n sub s, number of spins, capital T, total measurement time, T2 star, the dephasing time of the spins. And now we can compare these two expressions. This is the standard quantum limit. This is the photon shot noise limit. And we can see the difference is just this factor here in the denominator, C times the square root of eta. Based on the definitions of those variables, they're always less than or equal to 1. And we can see that this is kind of a measure of the readout fidelity of our spin system, or at least the optical readout fidelity of our spin system, C times square root of eta. Okay, so with that, we can now compare different types of qubit systems and decide when we'll choose one over another, let's say. So we'll start with the alkali metal vapor that I used to study as a PhD student. I already complained that these systems tend to be bulky, but they do have very long dephasing times at room temperature, typically on the order of second. And they tend to have very high readout fidelities. They use this kind of off-resonant Faraday rotation, have very high readout fidelities of the order unity. Maybe on the other side of the spectrum are organic molecules, which can be made in gazillion quantities, Avogadro's numbers quantities. They're obviously very small. And that can be really helpful when trying to detect individual molecules, for example. They tend to, unfortunately, have some stability issues at room temperature. So I said before, I want to be able to shine my laser light on it and have these things glow for weeks and years at a time. That's not typically possible. The dephasing times tend to be relatively short. That has to do with the energy level diagram that you use to try to see ODMR spectroscopy. And then the readout fidelities, also at room temperature, tend to be kind of small at the level of, let's say, 10 to the minus 4 or so. So in this context, the NV center in diamond is kind of like a middle ground. It's kind of like pretty good on each of these specs. So it's a point defect. Its electronic wave function is very localized. But it sits inside of a diamond host crystal. There needs to be some kind of gap between the actual wave function and the outer world. So it's not quite as, let's say, small as the organic molecules. But it is in the solid state host, which means we can do all the cool things that we talked about before with carving circuits, et cetera. It operates reasonably well at room temperature. The dephasing times are typically limited by the impurity concentrations of other types of spins inside the diamond, but they can range from 0.1 to, let's say, 100 microseconds, so a bit longer than the organic molecules. And then, if we were to just go into the lab right now and try to do ODMR spectroscopy with these NV centers, we'd probably get a readout fidelity at the level of about 10 to the minus 2, 1% or so. And then if we worked really hard, maybe we could get it down to a few tens of percent. So they fall kind of somewhere in between the atomic vapor and the organic molecules. OK, I gave a really simple picture of ODMR a second ago. With NV centers, the situation is a little bit more complicated. I'll just focus on the differences. So there's a ground electronic state and an excited electronic state. That can be excited optically. That's all great. The ground state turns out to be a spin triplet. The excited state is also a spin triplet. So there are 3 spin levels. And it turns out that even in the absence of a magnetic field, there's this kind of energy splitting between the ms equals 0 level and the ms equal plus or minus 1 levels of about 2.87 gigahertz. It turns out that that splitting is sensitive to temperature, which means that if you wanted to measure temperature, and that could be pretty interesting, you can just try to measure this spin transition at 0 magnetic field as accurately as possible using the ODMR tricks. But if you want to measure magnetic fields, it's actually just a little bit of a nuisance. So with the NV center, there's access to these singlet states. There's this non-radiative decay. The non-radiative decay turns out to be more probable if the spins start in m sub s equal plus or minus 1. They strongly couple through these singlet states. And then they tend to preferentially decay into the ms equals 0 state. So what it means is that if you turn on the laser light after a few optical cycles, the NV centers will all collect in this m sub s equals 0 state. And also that because of the same reason, if we leave the laser light on long, the brightness, the fluorescence intensity will be brighter if the NV centers are in the m sub s equals 0 state compared to the m sub s equal plus or minus 1 states. And this means that we can do ODMR spectroscopy. Now, unlike before, there's actually going to be 2 allowed spin transitions, one from 0 to plus 1 and one from 0 to minus 1. But the transition frequencies will split linearly in opposite directions as a function of magnetic field, and we can use that to detect magnetic fields. One more little caveat is that now this is the projection of the magnetic field onto the NV axis. So it's kind of like a vector magnetic field sensor detects one component of the magnetic field. And here's an example of an ODMR spectrum where you can see 2 different ODMR peaks for the 2 different spin transitions. OK, well, the research field has been pretty active, I don't know, maybe the last 15 years or so. And so people have applied this to study a wide range of problems. And here's just like a small snippet. It's actually a little bit of an old slide. You'll see like nothing is beyond 2017. So don't get upset with me if your favorite application isn't on here. But it's just kind of a snapshot. So people have put individual NV centers on scanning probe formats and imaged the vortices produced by high TC superconductors. People have laid down graphene nanoribbons and monitored, imaged the current flow through the ribbons and even managed to pick out little defects and things in the current flow. They've also managed to map out the very rich magnetic textures present in antiferromagnets. Our former research assistant professor, Abdulghani Ladoui, did this really cool experiment where he used a single NV center on a tip in a scanning probe format, and then used the temperature dependence of the zero field splitting to map out the thermal conductivity on some kind of nano-patterned solid state surface. People have managed to look at signatures of the nuclear magnetic resonance spectrum of protons inside of individual proteins. They've also detected electron spin labels through electron paramagnetic resonance of individual proteins. And then even managed to detect the magnetic fields produced by firing neurons in an individual sea urchin neuron model. So pretty wide range of applications, and I think I'm just going to talk about two that we're working on in my lab for the next 25 minutes or so. Any questions? Can I take questions now? Or any questions on any of that? Yeah?
When you have an ODMR spectrum, you get the same readout at two different frequencies. Is that a problem disambiguating that?
Let me just go back a second. So the question was?
You could get two of the same readout values at different microwave frequencies on an ODMR spectrum.
Oh, yeah, like on either side of the peak? That's a really good question. So let's see. I would say that often not, because often the changes in magnetic field we're looking for are very small. And so we'll, let's say, bias our system where we're here, and we're looking for changes that are so small that we know will stay on the same side. But ultimately, that is sort of a restriction on the dynamic range of the sensor. So you have to be kind of clever about tracking so that you can keep track of which side of the spectrum you're on. So that was a good question. Anything else? OK, we'll keep going. OK, so the first one I want to talk about is at like the very smallest length scales, and the next one will be at a very different length scale. So it's super resolution magnetic microscopy. This is research that's led by graduate student Nazani Mosavian and a graduate student Forrest Hubert. Here is a picture of part of the setup here. And the idea was as follows. So there kind of tends to be two types of formats for using NV centers to image magnetic fields. One is a scanning probe format, kind of like an AFM, or if you're used to that, or STM, where you have some kind of tip. It's got our individual spin qubit, and then there is a sample of interest. And by scanning the tip relative to the sample, we map out the local magnetic field 1 pixel at a time. And then another format, which is like called a wide field format, where we actually just take a normal epifluorescence microscope, and we image now not the fluorescence from the sample, but the image from, we image the fluorescence from a diamond cover slip. So it's got a thin layer of NV centers. We image the fluorescence from all of those NV centers on one shot onto a camera, and we sprinkle our magnetic sample on top, and by using microwaves to encode the magnetic information into the fluorescence brightness of the NV centers, we're able to get magnetic images of the entire sample all in one shot, let's say. So to make a comparison, a very crude comparison between the two methods, well, when it comes to spatial resolution, the scanning probe method tends to have very good spatial resolution at the level of, let's say, 40 nanometers or so. And the wide field method is a bit worse. It's limited by optical diffraction at the level of, let's say, 300 nanometers or so. When it comes to complexity, I would argue that the scanning probe method is a bit more complex. First of all, you need to get this kind of nanostructured diamond tip with an individual NV center at the tip. And then you also need to put everything in a vacuum and have everything very stable, et cetera, et cetera. There's some restrictions on the sample geometries and things like that. The wide field method is really pretty straightforward. It's just as simple as sprinkling things onto a cover slip, so it tends to be a fair bit simpler. when it comes to imaging speed, because the scanning probe method is not very sensitive, only uses a single spin, and it only acquires 1 pixel at a time. It's relatively slow, whereas the wide field method uses many NV centers and gets a full image in, let's say, 1 camera frame. So what we were wondering was whether there's a third method that, again, kind of falls like somewhere in between these two, sort of fits in the middle ground where it makes the trade-offs between these two methods. And the way we're going to do that is with super resolution, far field super resolution magnetic microscopy techniques. And the particular one we ended up settling on is something called charge state depletion microscopy, which works as follows. So we'll start with a focused laser beam. I'll just picture it as a circle. It's a Gaussian, of course, kind of shape in the image plane. And then I kind of didn't mention this before, but it turns out that there's at least 2 charge states of the NV center that are important. So all of the stuff I was talking about before was about the NV minus center. That has this really nice, stable, coherent spin levels in the ground state and all the energy levels, et cetera, that I talked about. There's this other charge state, the NV0, the neutral NV charge state, not particularly useful for sensing, but it can be exploited. And so what goes on is if we shine a green laser light on long enough, there will be some kind of steady state populations of NV0 and NV minus, and it turns out NV minus is a bit favored. So we'll have more population in the NV minus charge state. Then we're going to go in with a red donut beam with a wavelength of about 637 nanometers. This donut beams have 0 intensity in the center, right, and a high intensity in a donut shape outside. So in the high intensity region here, this asterisk, what goes on? Well, it turns out that when you shine this intense red laser beam, the NV minus centers tend to get converted to the NV0 state through this 2-photon process that involves photoionizing the conduction band. So they'll end up in this NV0 state, which is going to be our dark state. Meanwhile, the stuff at the center is just not perturbed by the donut beam at all. And so then we're going to go in with a weak Gaussian readout beam. And then, yeah, we said that the stuff at the center wasn't perturbed, so it's going to still be in this NV minus state from the reset. Now we'll go in with this weak readout beam. It's not quite a high enough intensity to do this 2-photon process and photoionize the NV center, but it is intense enough to get fluorescence from these NV minus centers. And so what we've effectively done is we've prepared a very small core of NV minus centers that's much smaller than the wavelength of the light. And so that's the trick that we're going to exploit to get to the resolution beyond the diffraction limit. And notice, because this is 637 nanometers, all of these NV0 centers on the outside, they're not excited. Their optical transition requires 575 nanometers or lower wavelength. So they're just dark to us. So that's the trick for CSD microscopy. We ultimately do this in a pulse way. So we start with the reset beam, then we apply the donut beam for some time tau d, and then we do this readout cycle. Now, this readout cycle, in a simple way, can just be looking at the fluorescence brightness, or we can do all of these clever pulsed ODMR techniques to extract, for example, magnetic information about the sample. And we only detect photons when the readout beam is on, not when these other beams are on. OK, so we're building off of previous work. I'll just quickly point out that folks had used this technique already back in 2010. They didn't quite understand why it worked, but they knew when they shined those laser wavelengths in that order onto the NV centers in a diamond that they were able to get super resolved images of individual NV centers. And people had managed very recently to do a kind of functional imaging. In this case, there were some silver nanowires put onto a diamond substrate. And they managed to kind of record the contrast of these ODMR peaks, which tells them something about the microwave field amplitude with a spatial resolution that was a bit better than what could be done with just ordinary confocal microscopy, so without the super resolution tricks. And the question that we asked was whether we could extend this method to create quantitative magnetic field maps with a high spatial resolution. And then, yeah, of course, the answer was yes, but only after a significant amount of work, as usual. So this is a picture of the setup. I won't bore you with all the details, but I'll point out Once we tried to get to very high spatial resolutions with high sensitivity over long periods of time, it turned out to be very important to stabilize our optical system. So the system started getting more complex. So we're not quite in the simple range of the wide field instrument. We're starting to get kind of close to the scanning probe in terms of complexity. But some other important parts of this setup. So here is our diamond cover slip. It's got a thin kind of planar layer of NV centers about 25 nanometers from the diamond surface. And then our favorite sample to study is something called a superparamagnetic iron oxide nanoparticle that Professor Fu already showed us how to study back in 2014. And it's a convenient sample because it's like very small nanoparticle that can be treated as though it were a point dipole. And the point dipole's direction can be controlled externally with our external magnetic field. So we can move it around and we can figure out exactly what's going on with our system. I think that's about it. OK, so in a first set of experiments, we just wanted to test whether the CSD microscope could work in our lab. We'd already seen it work in other ones. We just need to make sure it works for us. And what we did was we just took a diamond with a very low density of NV centers, and we measured what's called its point spread function. So we tried to measure the NV center is kind of like a point, and we tried to measure how big does it appear in our images after we scan around in X, Y, and Z. And indeed, we're looking at the lateral full width half max. That's kind of the width of these features here. And we see that as we increase the donut pulse length, the full width half max shrinks according to the equation that we expect. And then in the best case, we're getting kind of widths that are about 40 nanometers or so. So kind of deeply into the sub-wavelength regime where we wanted to be. And we can use that to resolve the fluorescence from individual NV centers that couldn't be resolved with confocal microscopy. So here is an example of the donut off. We're just doing a normal confocal microscopy. We get a spot on our image. Maybe we think it's just a single NV center. It looks pretty symmetric. But then when we turn on the donut beam and we do this super resolved imaging, we find out that actually it's two NV centers separated by about 150 nanometers or so. OK, now moving on to magnetic imaging. So now we're going to take the diamond with the dense layer of NV centers very near the diamond surface. And when we do this readout phase, we're going to sweep the microwave frequency, measure the ODMR spectrum. And then in that pixel, we're going to enter in the magnetic field value. And then we're going to repeat as we scan the sample in X and Y. So first, we do this without the donut beam on. We're just doing confocal microscopy. We get a magnetic image that looks like this. Sorry, I should have pointed out, this is an SEM of an individual spion that we put on our diamond with these fiducial markers that let us find the same one later. And so this is a magnetic image of that same spion. And you get this kind of characteristic dipole pattern. It goes like dark and then bright. It matches pretty well with what we would expect from a point dipole. And this is what happens when we turn the donut on. Now you have to be a little careful. You have to look at these scale bars, both the spatial scale bars and also the intensity scales, to see that anything interesting is happening. So you'll see that we've gone from 400 nanometer scale bar to 100 nanometer scale bar. So actually this whole image corresponds to this red box cutout here. So it's actually significantly higher spatial resolution. Matches also what we expected from simulation. Maybe the most important thing is if you notice this intensity scale. So the whole range before was about 20 microtesla. Now it's about 200 microtesla. So it's about an order of magnitude magnetically brighter. And that's not unexpected, but it's an important feature. So here's an example. We just take a line cut through these profiles and we plot it. And you can see the confocal one is this purple one. It's broader, and it's a smaller amplitude. And then the green one is the super resolution one. And probably the most dramatic thing is that, the larger amplitude. So this is not unexpected. We have a dipole. The magnetic field from a magnetic dipole falls off as 1 over the distance cubed. And by shrinking the size of the characteristic distance of the NV centers to that point dipole, we end up with a larger effective magnetic field, and so we get a larger signal amplitude. OK, we're able to do this with multiple spions. So here's an SEM of like a configuration of 3 spions like this. With the donut beam on, the magnetic image is a mess. But when we turn, when the donut beam off, the magnetic image is a mess. When we turn the donut beam on, we're able to see 3 dipole patterns that match the simulation. So these are kind of early results that show that this method works. There's a few drawbacks that I'll probably briefly touch on. One drawback is that we're getting this extra background emission, which becomes an issue. It reduces our sensitivity. Another is that another type of source of background is that I kind of gave this picture that we're completely able to deterministically control the charge state of these NV centers. Turns out when we use a high density of NV centers very close to a surface, it's not so deterministic. And that leads to problems. So we end up that these NV centers in the donut region that we wanted to be dark are actually somewhat contributing to the signal. So there's still some room for improvement, but here's kind of where I placed us on this table. So the spatial resolution in the magnetic images are about at the level of 100 nanometers or so. The complexity, I'm claiming on this slide is medium. Maybe it's kind of closer to the difficult side, right? This takes up a whole optical table, 2 PhDs to run it, et cetera. It's not so simple. The imaging speed, well, currently this is relatively slow. It's just like one laser beam moving around. But what we expect is that because now we have this far field super resolution method, it can be parallelizable. So we can use optical lattices or arrays of donut beams image onto a camera and have like kind of many bits of magnetic information collected at once. Okay, and then the second thing is all the way on a very different length scale. This is now trying to detect magnetic fields at the level of 10 to the minus 15 Tesla, or femtotesla. And this is work that was started by our former postdoc, Ilya Fishenko, and has been continued by our now, as of 2 or 3 weeks ago, Dr. Yasser Salani. So he recently defended his PhD about 2 or 3 weeks ago. So some of the motivation of detecting magnetic fields at the 10 to the minus 15 Tesla level are what I talked briefly about before, this magnetoencephalography, the imaging of the brain currents, which can be useful for monitoring the disease progressions of like epilepsy and stuff. And something called NQR spectroscopy, so nuclear quadrupole resonance spectroscopy, which can be useful both for fundamental material science studies and then also for like detection of illicit drugs and explosives and things like this. And in general, these things require very high sensitivities at the level of 1 or 10 femtotesla root seconds. The frequency ranges are very different for the two, but I'll talk briefly about them. Okay, so now we need to go back to this sensitivity equation. This is this photon shot noise limited sensitivity. And I'm going to rewrite it. So now I have delta B min square root of t. T was the integration time. I'm just going to move it out here. We're going to assume that everything improves as the square root of integration time. And we see that there's like 3 terms here. So there's this 1 over gamma. That was the gyromagnetic ratio. That's like a term that tells us how does the qubit convert changes in magnetic field to changes in the ODMR transition frequency or the spin frequency. There's this other term, 1 over c root eta. We talked about that. That's like the readout fidelity. And then there's another term, 1 divided by the square root of NNV. That's the number of NV centers times T2 star. That was the dephasing time. And that's kind of limited by, let's say, materials properties. So we got to choose one of these terms at least to work on. But there's something to, oh, sorry. So first we're going to do calculation, sorry. So we take some typical numbers here for the various parameters. The only thing that is not typical here is the number of MV centers. So this is actually 10 to the 15 MV centers, corresponds to typical concentration of 6 parts per million, but in a 1 millimeter cubed sensor size. So this is not typical, this is high. But even with this very large number of MV centers, we're still kind of on the edge of where we want to be, right? So now we have a sensitivity of 100 femtotesla root seconds. I mentioned before, we'd rather be at 1 to 10, but even with this high number. But there's another thing to pay attention to, and that is related to the laser power. So if we assume that every NV center should absorb at least 1 photon per T2 star, per dephasing time, we can define a minimum laser power needed to reach the photon shot noise limit. And it's very much a minimum because actually in reality you often need many more than 1 photon removed from the laser beam to efficiently do ODMR spectroscopy. But nevertheless, we can define this minimum laser power HC over lambda times NNV divided by T2 star. We plug in the wavelength of the laser beam that we use, and we find to get to this 100 femtotesla root seconds from before that we need 3 kilowatts of laser power. That's a lot. So this picture that I got from some Google image search is a laser cutter. It only uses 250 watts of laser power. So you can imagine the 3 kilowatts is just not going to happen. Yeah. So we need to rethink things. We can't just naively scale this system up to more and more spins and hope that things will work. And so what we did in my group maybe 4 or 5 years ago is we started to wonder, okay, other people are working on the material properties. We'll wait until they get us better diamonds or something. The readout fidelity, we can improve it a little bit here and there, but it's ultimately not going to be so different from what it is now. But what about this term here that converts changes in magnetic fields to change in spin frequency? Can we do something here? It's a little bit crazy because gamma, this thing in the denominator, is like kind of a fundamental constant. It's the gyromagnetic ratio of the electron. So it sounds a little bit crazy, but nevertheless, the answer was yes, we can modify that term. And the way that we do that is we use these magnetic flux concentrators. So basically, they're ferromagnetic structures that collect magnetic flux from a much larger area and concentrate it into our little diamond sensor at the center here. And so, yeah, like the magnetic field externally can change only by a little bit, but it gets concentrated into the diamond, and that leads to larger shifts of the ODMR peaks at the level of, let's say, about, I think it's, enhancement factor is a level of like 300 or so. So that was pretty cool. It worked. We found some surprising things, like everything worked better than usual. It's like really rare kind of experiment. So the enhancement factors that we got were the same as we modeled. That was kind of a nice surprise. And we also, we're sticking this huge chunk of ferromagnet next to our femtotesla sensor. Like, we figured all kind of things could go wrong, for example, hysteresis, but they didn't. We saw negligible hysteresis. So there's almost no memory. We can change the magnetic field all over the place, and the NV sensors will just read the current magnetic field without a history. Here's an example of running this thing as a magnetometer. We did some different things. I think I will skip over a few of the details. I'll just direct you to this blue curve. So this blue curve is the experimental curve. Probably the first thing you see when you see this curve, so this is the magnetic noise as a function of frequency on a log-log plot. Probably the first thing you see is like all these spikes, right? Well, these are 60 hertz and harmonics and a couple of subharmonics. So we do use magnetic shielding to try to suppress them, but these things are there all the time. So we suppress them by about a factor of 100, and they're still super prominent. But the largest peaks in this spectrum, this one here in the blue curve, is the one that we applied on purpose with our own set of coils. That was this test field that we used to calibrate our axis. So ultimately, when we measure like the noise floor where there are no spikes, we find something like 900 femtotesla root seconds, which is pretty close to the photon shot noise limit. When you use these flux concentrators, you have to pay attention to thermal noise that leads to like domain wall motion that leads to magnetic noise. That's this pink curve. We're not yet limited by that, but it's something to look at. So that's what happened here. So this frequency range was in the low frequency, like 1 hertz to 1,000 hertz. And then at the time, 2020, when we published this paper, we kind of took all of the different experiments that had explored the sensitivity of NV center magnetometers, and they were these points here, and then this red star is where our work placed us on this map. So a bit less than a picotesla, so a few hundred, 900 or so femtotesla root seconds, which was better than before, but still not where we really want to be, which is down here for things like magnetoencephalography. Okay, so for RF magnetometry, that was the thing that we did most recently with Yasser. And the thing that we pointed out was like, okay, if we take the sensitivity equation, we have this value T2 star. We know if we're detecting magnetic fields at a higher frequency, we can do these clever microwave pulse sequences that replace T2 star with T2. And as with many spins in solids, T2 tends to be much, much longer than T2 star, and so that should give us some improvement in the overall sensitivity. Okay, I'll hurry up. There was an initial question about whether the type of ferrite we were using for the flux concentrators would work above 1 megahertz. This is this manganese zinc composite called MN60. Tends to be only considered good for low frequencies because its magnetic properties change abruptly above about 1 megahertz. We weren't sure if it was going to work above 1 megahertz. Turns out it does. Turns out that our properties are a little bit different from the manufacturer's spec sheet. Setup is similar to the one I talked about before. We just replaced the magnetic shielding now with aluminum shielding, so it's blocking the RF magnetic fields. And we use this kind of complicated sensing protocol, and I probably will abstract most of it away. So we'll say, okay, so here is this oscillating magnetic field we're trying to detect, let's say at around 1 megahertz or so. We go in with these series of laser pulses. They're going to measure the fluorescence of the NV centers, and then we apply this kind of set of phase synchronized microwave pulses. And the whole point of this pulse sequence is that the fluorescence brightness becomes proportional to the initial instantaneous magnetic field at the start of this sequence. So the fluorescence brightness here was the instantaneous magnetic field at the start of this sequence. The fluorescence brightness here was the instantaneous magnetic field at the start of this sequence, et cetera, et cetera. And what we can see then is that we're kind of subsampling this oscillating waveform from before, and we get this alias down version of the AC magnetic field encoded into the oscillations of the fluorescence brightness. So that's how this sequence works. We did a set of experiments, like one with the flux concentrators and one without them. We found that indeed we were getting relatively large enhancements, about the level of 300 or so. And here's a picture of the noise spectrum. So far fewer spikes when you're detecting in the megahertz or the few hundred kilohertz regime, kind of nice. Just need a little bit of aluminum shielding. You can see with no cones, the sensitivity is about, I think it was 18 picotesla root seconds. And then with the cones, we're getting somewhere around 70 femtotesla root seconds. So a significant improvement over the previous work. We studied the frequency response, and we found that we were able to get the same enhancement factor all the way up to like about 4 megahertz, which wasn't expected because the highest enhancement factor that's physically possible is at least the relative permeability of the material. And on that plot, I showed like the relative permeability was falling off a cliff above 1 megahertz, so it can't possibly have fallen off so quickly. Otherwise, we wouldn't get such a high enhancement factor. And indeed, we found like that the bandwidth of these sensors tends to go from about 70 kilohertz up to about 3.6 megahertz or so. So the sensor works in a pretty broad range of frequencies. So this is where that places us on this plot here. That's the open star here. So also, there was a lot of other works that were done in the interim. So there were more points out here at the higher frequencies. But we saw like a significant improvement. Still not quite at this kind of 10 femtotesla level that we like to be, but still useful for a few things. And I think that I will just quickly flash that thing that we did. We did something called nuclear quadrupole resonance spectroscopy of powders. It's basically doing NMR spectroscopy in the absence of a magnetic field, and you can still get this kind of unique fingerprint that can tell you like what is the thing that you're looking at. And people have looked at heroin and cocaine and fentanyl and TNT and all kind of crazy stuff. We chose a standard sample, sodium nitrite. We looked at this NQR line at 3.6 megahertz. We compared our magnetometer with a typical coil inductive based readout method. We used a very similar pulse sequence to before, except for now we add a pulse that's resonant with that 3.6 megahertz spin transition to start the nuclear spins processing. And then we detect the AC magnetic field that they produce. And we take a Fourier transform, and we get a spectrum. So here's example data when we did this with sodium nitrite. On the red, you get these high oscillation frequency. On the bottom is that's with the coil readout. With the NV readout, you get this alias down version, but nevertheless kind of very similar properties, exponential decay at the level of 800 microseconds or so. When you take the Fourier transform, they also kind of line up exactly as expected, so this seems to be working reasonably well. It turns out that these NQR transitions are very sensitive to temperature. We kind of noticed this accidentally, but it turns out that this is very well studied in literature. And just a small change of, what is this, like 2 degrees or so leads to like a several line width shift in the NQR resonance frequency. And so we were able to plot out the temperature dependence, and it all agreed with previous work. Something interesting about MV centers is that because they can be optically polarized very quickly, they have a very short dead time, meaning we can apply large RF pulses and then immediately, almost immediately, within about 10 microseconds, start detecting the NQR signals from the sample. Turns out to be important if the sample magnetization decays very quickly after a pulse. Oops, wrong way. And we do a number of other things Professor Fu alluded to in the introduction. I just flashed them up here quickly so you can take a peek. And then I will finish just by acknowledging the members in our research group and collaborators. And there's one person in particular who I haven't yet shown a picture of. This is our postdoc, Dr. Janis Schmitz, who's been in the lab for 5 years or so. He started as a visiting graduate student, continued as a postdoc, played an extremely important role in all of the work that I showed. We really couldn't have done it without him, so I want to make sure that I can show his face here. And with that, I'm happy to take any other questions.
Thank you. I think we have time for 1 or 2 short questions, and then people can go and people can stay and ask questions as you like. Okay, I'll kick it off. With the flux concentrators, how uniform is that amplification? Like, do you have to worry about the homogeneity?
Yeah, it's like really uniform, actually. Maybe you can't fully appreciate it in the map, but it is. Let's see, where's the map? Yeah, here's the map. So yeah, it's quite uniform all throughout the gap. It only starts to kind of diverge at the edges. So this is like the enhancement factor in space. So they suppress magnetic fields that are transverse to the cone axis, and they only enhance along the cone axis. And then, yeah, it's quite uniform. Now, if you had a wedge, like instead of a flat gap, if you had a wedge for some reason, then that would lead to some significant non-uniformity.
Other questions? Horace?
How many samples of MN60 did you find this unexpected improvement that you
Oh, that's a good question. I think we just tested 2 sets of cones. Like at one point the thing broke, and we made a second one. So yeah, that spec sheet, I mean, it's maybe not fair comparisons. That spec sheet is some bulk formulation. These things are composites, so you can see there's like all these little crystals that are formulated here. So I don't know that there's any reason to expect that one set should be exactly the same as the other. But yeah, I guess the 4 cones that we tested seem to have a bit higher frequency performance.
Why did you stop at 4 megahertz?
That's just related to the pulse sequence. So it's related ultimately to like the Rabi frequency that we get with the electron spins. So you can see like in this pulse sequence, the frequency of the oscillation that we detect, we have to be able to fire 2 microwave pulses during that time, and also have enough gap in between them to detect the magnetic fields. And so, yeah, our pulses were about 25 nanoseconds or so, and that meant we could go up to 4 megahertz without much of an issue, and above was hard.
Okay, if there's no more questions, let's thank Victor one more time, and people are welcome to come down and chat.